Approximately 307 million years ago, during the late Carboniferous period, a vast and largely unbroken forest covered much of what is now equatorial Europe and North America. The continents, still locked in configurations entirely unlike the modern world, carried across their low-lying interiors a climate of persistent heat and moisture, conditions that had sustained this forest for tens of millions of years. There was no seasonal cold to impose limits. There was no prolonged drought to reset the cycle. The forest simply continued, generation after generation, accumulating biomass on a scale that the modern world no longer supports. The atmosphere above this forest was measurably different from the one that exists today. Oxygen concentrations had risen to approximately 35% of total atmospheric composition, compared to the 21% that characterizes the present era. This elevation was not incidental. It was the direct biochemical output of the forest itself, a product of photosynthesis operating across an area, estimated in the tens of millions of square kilometers, releasing oxygen faster than geological processes could remove it. The planet's chemistry had been altered by life, and life, in turn, was being altered by that chemistry. The dominant organisms shaping this landscape were not trees in any sense that would be immediately recognizable today. Lepidodendron and sigillaria, giant lycopodids or scale trees, rose to heights between 30 and 50 meters. Their trunks, covered in distinctive diamond-shaped leaf scars, grew with a rapidity that modern arboreal species do not approach. Before we go further, take a moment to consider where you're watching, from which country, and how distant it is from the ancient forest we're about to enter, a place where towering vegetation concealed predators, giant insects, and creatures unlike anything found today. If these journeys into lost worlds keep capturing your imagination, consider subscribing to continue the adventure. It's always fascinating to see how far these stories travel. Lower the lights, settle into stillness, and let the modern world fade as shadows gather beneath immense trees. Strange calls echo through the undergrowth, and something unseen moves quietly through the forest beyond, reaching full height within a matter of years and producing little in the way of lateral branching until their upper extremities. The canopy they formed was dense and relatively uniform, filtering the light that reached the forest floor to a fraction of its original intensity. At ground level, illumination was limited and diffuse. These lycopod trees reproduced through spores rather than seeds. Their reproductive structures, strobili, cone-like organs borne at the tips of upper branches, released spores into an atmosphere already saturated with moisture. Germination depended on standing water, a resource that the Carboniferous lowlands provided in abundance. Vast peat swamps extended across basin after basin, their surfaces broken by the emergence of new growth and the slow subsidence of decaying plant matter. The accumulated organic material did not decompose efficiently. The microbial and fungal communities capable of breaking down lignin, the structural compound that gave these trees their rigidity, had not yet evolved to the level of effectiveness that later periods would produce. Organic carbon was therefore buried in extraordinary quantities, a process with consequences that extended far beyond the forest itself. Beneath the canopy, the understory was occupied by a different assemblage of plant forms. Ferns of multiple lineages covered the ground in dense mats, their fronds reaching heights of 2 to 3 meters in some species. Calamites, giant horsetails, relatives of the small and inconspicuous horsetails, still present today, in modern wetlands, grew in dense stands along waterway margins and in areas of periodic flooding, reaching heights of up to 20 meters. Seed ferns, or pteridosperms, occupied intermediate layers, their foliage creating additional tiers of vegetative density between the ground and the high canopy. The result was a vertical stratification of plant life that created distinct microenvironments. At every level, each with its own thermal characteristics, moisture gradients, and light availability. The forest floor itself was in a state of continuous biological process. Fallen trunks of lycopod trees accumulated in layers, slowly compressing under the weight of subsequent growth. Where standing water was present, this organic material entered anaerobic conditions almost immediately, preserving structures in extraordinary detail. Where the ground was drier, decomposition proceeded through the action of invertebrate detritivores and primitive fungal networks. The distinction between these two zones, wet and dry, preserved and decomposed, would prove significant over geological timescales, determining which portions of the forest would eventually contribute to the coal seams that geological surveys have since mapped across multiple continents. The fauna of this forest was governed, in fundamental ways, by the elevated oxygen concentrations that the plant community had produced. In arthropods, animals whose respiratory systems rely on passive diffusion of oxygen through a network of tubes called tracheae, the concentration of atmospheric oxygen directly constrains maximum body size. At 35% oxygen, the diffusion gradients that supply interior tissues with adequate oxygen could sustain body volumes far beyond what present atmospheric conditions permit. This single physiological relationship explains, in large part, why the arthropod fauna of the late Carboniferous achieved body dimensions that have never been repeated in the subsequent 300 million years of insect evolution. Among the most structurally prominent arthropods of the forest floor were the myriapods, specifically members of the genus Arthropleura, the largest terrestrial invertebrate that has so far been documented in the fossil record. Trackway evidence and body fossil fragments indicate individuals reaching lengths of 2.5 meters with a body width approaching 50 centimeters. These were not predators. The morphology of their mouthparts and the isotopic signatures preserved in their fossilized remains both indicate a diet composed primarily of plant material, decaying vegetation spores, and the soft tissues of ground-level plant structures. They moved through the lower forest as processors of organic material, their passage leaving distinctive parallel trackways in the soft sediment that paleontologists have since recovered from sites across what is now Scotland and Pennsylvania. The mobility and metabolic demands of these large myriapods were supported by the oxygen-rich atmosphere in a direct and measurable way. Tracheae in arthropods are not actively pumped. In the manner of vertebrate lungs, oxygen moves through them by diffusion, driven by concentration gradients. At higher oxygen concentrations, those gradients are steeper and diffusion proceeds more rapidly, allowing oxygen to reach tissues located deeper within a large body. At present atmospheric concentrations, a body the size of Arthropleura would not receive sufficient oxygen to its interior tissues through passive diffusion alone. The physics simply would not support it. In the late Carboniferous atmosphere, they did. Above the ground layer, the forest interior was occupied by a diverse assemblage of smaller arthropods, cockroach-like insects whose forms have been documented extensively from Carboniferous deposits. Early arachnids occupying the role of ground-level predators, and a variety of detritivore species exploiting the continuous supply of decaying plant material. Cockroach species of this period, some reaching body lengths of 9 to 10 centimeters, were among the most numerous insects in the forest. Interior, their flattened body forms and rapid locomotion, making them effective exploiters of the confined spaces between fallen logs and compressed leaf litter. Their abundance in the fossil record likely reflects both their actual population densities and the preservational conditions of the coal swamp environment, which was particularly effective at capturing chitinous exoskeletons. The vertical dimension of the forest, that layered stack of vegetation extending from the waterlogged ground to canopy heights of 50 meters, created a set of ecological zones that operated under genuinely different physical conditions. At ground level, temperatures were moderated by shade, humidity was consistently high, and oxygen was present concentrations that, by modern standards, would be considered extreme. At canopy level, light was abundant, wind movement was greater, and evapotranspiration, The combined process of evaporation from plant surfaces and transpiration from leaf structures contributed significantly to the local moisture cycle. Between these two extremes, intermediate zones supported organisms with correspondingly intermediate ecological requirements. The flying insects that occupied the canopy and the airspace above it represent some of the most structurally extraordinary animals that the fossil record has preserved. Griffinflies, members of the order Meganeura, commonly referred to in earlier literature by the genus name Meganeura, possessed wingspans documented at up to 70 centimeters. These were not gliders. Wing venation patterns indicate musculature capable of active powered flight, with maneuverability sufficient for aerial predation. They occupied the role of apex aerial predators in an environment where no vertebrates had yet achieved sustained flight, and where their size gave them a decisive mechanical advantage over every other flying organism present. The aerodynamic requirements of flight at this scale were, in part, by the elevated atmospheric oxygen that supported the respiratory demands of large metabolically active tissues. The swamp margins, the transitional zones between standing water and relatively dry forest interior, were among the most ecologically dense portions of the landscape. Here, aquatic and terrestrial organisms intersected in a zone of concentrated biological activity. Early tetrapods, four-limbed vertebrates that had emerged from fully aquatic lineages tens of millions of years earlier, occupied this marginal habitat with increasing effectiveness, their anatomy reflecting a body plan still strongly tied to water for reproduction and thermoregulation, but increasingly capable of exploiting terrestrial food resources. These animals, some reaching lengths of 1.5 to 2 meters, occupied a position in the ecosystem that combined aquatic ambush predation with limited terrestrial mobility, making the shallow water margins of the forest swamp zones of particular ecological intensity. The forest, considered as a single integrated system, functioned through a set of interlocking processes that reinforced one another over geological time. Plant growth sequestered carbon. Sequestered carbon altered atmospheric chemistry. Altered atmospheric chemistry permitted larger arthropod body sizes. Larger arthropods processed organic material at scale. Processed organic material cycled nutrients back into the system. The system was not static. It fluctuated in response to local variations in precipitation, sediment dynamics, and the gradual tectonic movements that shifted drainage patterns across the lowland basins. But its fundamental character remained consistent across millions of years. What made this forest extraordinary was not any single organism or any single process, but the convergence of conditions, atmospheric, geological, and biological, that had no precedent before the Carboniferous and have not recurred since. The elevated oxygen, the absence of effective lignin decomposers, the warm and stable equatorial climate, the shallow basin topography that preserved organic material rather than eroding it. Each of these factors contributed to an environment in which life operated at scales that the planet has not replicated. The forest was, in measurable and demonstrable terms, a singular event in Earth's biological history. Above the canopy of the Carboniferous forest, at altitudes where the uppermost branches of the lycopod trees gave way to open air, a distinct and largely separate ecological zone operated under its own set of physical rules. The density of vegetation below created a thermal boundary. Warm, moisture-laden air rising from the swamp floor met the relatively drier airspace above the canopy, producing persistent updrafts along the forest margins and above the larger clearings created by fallen trees. These columns of rising air were not incidental features of the landscape. They were structural components of the aerial environment, and the organisms that evolved to exploit them did so with a mechanical precision that the fossil record has preserved in considerable detail. Meganeura, the order of large griffinflies whose members include the most extensively documented of the giant Carboniferous insects, were active, powered flyers. This distinction is significant. Wing venation in recovered specimens shows a complexity and cross-bracing architecture, consistent with musculature capable of generating sustained thrust, not merely gliding on available air currents. The wing surface area of a griffinfly with a 65-centimeter wingspan, within the documented range for this group, provided sufficient lift at the air densities of the late Carboniferous atmosphere to support a body mass estimated between 100 and 150 grams. For context, that body mass falls within the lower range of modern passerine birds. These were not lightweight aerial drifters. They were heavy, fast, and mechanically capable animals operating in an environment that offered them no aerial competition from vertebrates. The absence of flying vertebrates during the Carboniferous is a structural feature of the ecosystem with direct consequences for the griffinflies. Birds would not appear for another 230 million years. Pterosaurs, the first vertebrates to achieve powered flight, were still more than 80 million years in the future. The airspace above the Carboniferous canopy was occupied exclusively by insects, and within that insect community, the griffinflies held a size and speed advantage over every other flying organism present. Their compound eyes, large relative to their head capsule, as in modern ordinate relatives, provided wide-field visual coverage suited to detecting movement against a complex background. Their forelegs, positioned anteriorly and equipped with spines, formed a grasping back geometry consistent with aerial prey capture observed in modern dragonflies, a group that, despite its much smaller size, retains a prey capture success rate among the highest recorded for any predator. Prey for griffinflies consisted primarily of other flying insects, a community that, by the late Carboniferous, had diversified substantially. Early members of lineages ancestral to modern cockroaches, mayflies and stoneflies occupied the lower and middle airspace. Some of these insects reached body lengths of 5 to 8 centimeters, large by modern standards, but well within the capture range of a griffinfly, operating at 65 centimeters wingspan. Prey detection likely occurred at distances of several meters, with pursuit sequences covering distances of 10 to 30 meters based on the flight dynamics inferred from wing morphology. Capture took place in the air, with the prey being consumed either during flight or after the griffinfly landed on an elevated surface, a behavior well documented in modern odonates. The hunting range of griffinflies extended across multiple habitat types within the broader forest, landscape, open swamp surfaces where standing water reflected light and smaller insects congregated near aquatic vegetation represented concentrated foraging areas. Forest clearings where fallen lycopod trunks had opened gaps in the canopy created sunlit patches that attracted insect activity and provided griffinflies with unobstructed flight corridors. The margins between dense forest and open water were particularly productive zones, combining the thermal updrafts generated by differential heating with high concentrations of smaller flying prey. Evidence from fossil assemblages at several European Carboniferous sites shows griffinfly remains concentrated in depositional environments, consistent with swamp margin habitats, supporting the inference that these zones were preferred foraging areas. The physiological basis for griffinfly body size, like that of other giant Carboniferous arthropods, rests on the mechanics of tracheal respiration in an oxygen-elevated atmosphere. At 35% atmospheric oxygen, the diffusion gradients through tracheal tubes could sustain active flight muscle tissue in a body with a thorax of the dimensions documented in Meganeura specimens. Experimental and computational work on modern dragonfly flight physiology has established baseline relationships between tracheal diameter, oxygen concentration, and maximum sustainable tissue volume. Extrapolating these relationships to Carboniferous atmospheric conditions produces body size maxima, consistent with the fossil record, a convergence between physiological modeling and direct paleontological evidence that strengthens confidence in the oxygen body size hypothesis. It is worth noting that body size in the griffinflies was not uniform across the group, or across geological time within the Carboniferous. Earlier members of the lineage were smaller, and maximum body sizes appear to have tracked, with some lag, the gradual rise in atmospheric oxygen that characterized the mid to late Carboniferous. This temporal correlation adds a dynamic dimension to the relationship between atmospheric chemistry and arthropod size, one that suggests body size was continuously responding to environmental conditions rather than simply reflecting a static upper limit. As oxygen concentrations fluctuated, so over evolutionary timescales, did the maximum sizes achievable by trachea-dependent flyers. For the smaller insects of the Carboniferous airspace, the presence of griffinfly scale predators imposed selection pressures with measurable consequences. Escape behavior in modern insects, rapid directional changes, erratic flight patterns, sudden drops toward vegetation, is understood as an evolved response to aerial predation. The structural diversity of wing venation patterns observed across Carboniferous insect fossils may reflect, in part, an evolutionary arms race between predator capture efficiency and prey evasion capability. The physiology of escape, dependent on rapid neural signal transmission and fast twitch, flight muscle activation, was itself influenced by available oxygen, creating a system in which the same atmospheric conditions that enabled predator gigantism also enhanced the physiological performance of potential prey. The canopy environment that griffinflies dominated was not a passive backdrop. Lycopod trees, reaching their structural maximum during this period, produced a surface topography at 40 to 50 meters elevation that included exposed branch surfaces, spore-bearing structures, and the upper faces of broad, strap-shaped leaves. These surfaces collected solar radiation and retained heat, creating temperature differentials relative to the shaded forest interior below. Air movement at canopy level, driven by these differentials, and by the broader regional wind patterns of the equatorial Carboniferous climate, provided the energetic substrate that made sustained aerial activity metabolically viable for large-bodied flyers. The griffinflies did not merely tolerate this environment, their body plan was, in measurable terms, adapted to exploit it. What the fossil record preserves of griffinfly biology is necessarily incomplete. Soft tissue, behavioral sequence, and metabolic rate leave no direct trace in Carboniferous coal deposits. What remains are wings, occasionally partial body impressions, and the indirect evidence embedded in the morphology of those structures. From these fragments, a functional picture can be assembled with reasonable confidence, an animal operating at the upper size limit permitted by atmospheric chemistry, exploiting an aerial niche with no vertebrate competitors in an ecosystem that provided both the thermal infrastructure and the prey base necessary to sustain it. The griffinflies were not anomalies. They were the predictable outcome of a specific set of physical and ecological conditions converging at a specific moment in Earth's history. At ground level, below the thermal gradients of the canopy, and beneath the aerial zones occupied by flying predators, the Carboniferous forest floor operated as a distinct and largely self-contained ecological system. Light penetration at this depth was minimal. Estimates based on canopy density modeling suggest that less than 2% of incident solar radiation reached the ground's surface in areas of closed lycopod canopy. The result was an environment defined not by photosynthetic energy capture, but by the slow, continuous processing of organic material falling from above. Dead fronds, shed bark panels with their characteristic diamond-shaped scar patterns, spore masses, and the compressed remains of fallen trunks accumulated in layers across the swamp floor, creating a substrate of extraordinary biological richness. This organic accumulation was the foundational resource of the ground-level food web. The organisms that processed it, detritivores in ecological terminology, occupied a functional role of considerable importance. By mechanically fragmenting large organic structures into smaller particles, they increased the surface area available to microbial decomposition, accelerating nutrient cycling and influencing the rate at which carbon either entered the atmosphere or became buried in anaerobic sediment. In the Carboniferous, where the microbial capacity to decompose lignin was limited compared to later periods, the mechanical contribution of large detritivores was proportionally more significant than it would become in subsequent ecosystems. The largest detritivore operating in this system, and the largest terrestrial invertebrate documented anywhere in the fossil record, was Arthropleura. Members of this genus belonged to the myriapod lineage, a group that includes modern millipedes and centipedes, though Arthropleura's closest living relatives are millipedes rather than the predatory centipedes. Its body plan consisted of a series of articulated tergite plates, broad, overlapping dorsal segments, arranged along a body axis that, in the largest documented individuals, reached approximately 2.5 meters in length and 50 centimeters in width. The number of leg pairs varied across growth stages, with larger individuals possessing in excess of 30 pairs of walking legs, each contributing to a locomotive system capable of moving the animal's considerable mass across uneven terrain with measurable efficiency. Fossil trackways attributed to Arthropleura have been recovered from multiple Carboniferous sites, most notably from sandstone deposits in Northumberland, England, and from comparable formations in Nova Scotia and several Central European localities. These trackways preserve parallel rows of leg impressions spaced at intervals consistent with the reconstructed leg geometry of the animal, and their width, up to 50 centimeters in the largest examples, provides an independent confirmation of body size estimates derived from fragmentary body fossil material. The substrate in which these trackways were formed indicates that Arthropleura moved across relatively firm, partially dried sediment surfaces adjacent to swamp margins, suggesting that its activity range extended beyond the permanently waterlogged zones into drier forest interior areas. The diet of Arthropleura has been a subject of scientific examination, and the available evidence converges on a plant-based diet. Mouthpart morphology in recovered specimens, where sufficient preservation exists, shows mandibular structures consistent with processing soft, plant tissue, spores and decaying vegetation, rather than the more robust, piercing or crushing morphology associated with predation on other animals. Isotopic analysis of fossilized cuticle material, where available, supports a diet low in animal protein. Spore masses have been identified within gut regions of at least one exceptionally preserved specimen, providing direct evidence of plant reproductive material as a dietary component. Taken together, these lines of evidence indicate that Arthropleura was a large-bodied herbivore and detritivore rather than a predator, a functional role with significant implications for its ecological impact. The passage of an animal of Arthropleura's dimensions through the forest floor environment would have had measurable physical consequences. Its movement across accumulated leaf litter and decaying wood would have fragmented organic material mechanically, mixing surface layers and exposing interior sections to microbial activity. In modern ecosystems, large soil invertebrates perform analogous functions. Earthworms, for instance, are understood to significantly accelerate nutrient cycling through their processing of organic material. Arthropleura, operating at a body mass estimated between 10 and 50 kilograms depending on the size of the individual, would have performed this function at a scale without modern equivalent among invertebrates. The physical conditions that permitted Arthropleura to reach the Ars dimensions are the same conditions that governed body size across the giant arthropod fauna of the Carboniferous. Tracheal respiration, as previously established, imposes a size ceiling defined by the rate at which oxygen can diffuse through the tracheal network to supply interior tissues. At 35% atmospheric oxygen, that ceiling was substantially higher than at present concentrations. For a millipede-grade body plan, in which the tracheal network is distributed along the body's length rather than concentrated in a thoracic region, as in insects, the elevated oxygen concentration allowed the addition of body segments and the scaling of existing segments to dimensions that the diffusion physics of a 21% oxygen atmosphere would not support. There is an additional structural considerations specific to myriapod body plans that may have contributed to Arthropleura's achievable size. The segmented architecture of myriapods distributes respiratory demand along the body's length, with each segment maintaining its own tracheal supply. This modular arrangement means that the diffusion distance from the tracheal opening to the most metabolically demanding tissues in any given segment remains relatively constant regardless of total body length. Increasing the number of segments, therefore, does not proportionally increase the maximum diffusion distance that any single tracheal keel branch must span. This may have provided myriapod-grade animals with a structural advantage in reaching large body sizes, relative to insects, where all flight musculature, the most metabolically demanding tissue, is concentrated in a single thoracic region. The forest corridor through which Arthropleura moved was structured by the spatial arrangement of lycopod trunks, which grew at relatively regular intervals determined by spore dispersal distances and competitive dynamics for light and water. At ground level, these trunks, typically 1 to 2 meters in diameter at their bases, created a series of interconnected spaces through which a 2-5-meter animal could navigate with body flexion distributed across its many articulated segments. Trackway evidence indicates relatively straight-line movement in open areas, with course corrections appearing in the trackway record where obstacles were encountered. The animal's low center of mass and wide body provided gravitational stability, and the large number of leg contacts with the substrate at any given moment ensured traction across surfaces of variable firmness. The ecological role of Arthropleura within the Carboniferous forest floor system was not that of an apex predator or a structurally dominant organism in a competitive sense. It was, rather, a high biomass processor, an animal whose large size allowed it to consume and fragment organic material at a rate and scale that smaller detritivores could not approach individually. Its presence in the ecosystem represented a concentration of detritivore function into a single body plan, made possible by atmospheric conditions that no subsequent geological period has replicated. When those conditions changed, when oxygen concentrations began their long decline toward the end of the Carboniferous and into the Permian, the physiological foundation that permitted Arthropleura's body size was progressively withdrawn. The fossil record reflects this. Arthropleura trackways and body fossils become absent from deposits formed after the late Carboniferous, marking the disappearance of the largest terrestrial invertebrate that Earth's ecosystems have so far produced. The wetland margins of the Carboniferous forest were not transitional zones in any passive sense. They were ecologically dense environments where the boundary between aquatic and terrestrial life was actively contested by organisms operating at the upper limits of their respective physiological tolerances. Water depth in these marginal zones varied from a few centimeters to perhaps 1-5 meters across distances of tens of meters, shifting seasonally and with the gradual subsidence of underlying peat layers. The substrate beneath the water surface was unstable, a compressed accumulation of partially decomposed plant material that offered inconsistent support and concealed the boundaries between solid footing and zones of sudden depth. For any animal moving through this environment, the physical landscape itself presented continuous navigational difficulty. The vegetation at these margins was dense and structured in ways that reduced visibility to short distances. Calamite stands, the giant horsetails reaching heights of 15 to 20 meters, grew in concentrated clusters along waterway edges, their vertical stems creating screens that broke sight lines both horizontally and vertically. Fern mats extended across the water surface in shallower areas, their fronds providing visual concealment for organisms beneath. The combination of limited light penetration, surface obscuration by floating vegetation, and the acoustic dampening effect of dense plant material created an environment in which detection of other organisms depended heavily on close-range sensory systems, vibration detection, chemoreception, and pressure sensitivity, rather than long-distance vision. It was in precisely this environment that the early tetrapods of the Carboniferous achieved their highest ecological densities. These animals are four-limbed vertebrates descended from lobe-finned fish lineages that had transitioned to periodic terrestrial locomotion during the preceding Devonian period, were not fully terrestrials in their biology or behavior. Their reproduction remained tied to water, their eggs lacking the amniotic membrane that would later allow vertebrates to reproduce on dry land entirely. Their skin, while more resistant to desiccation than that of their fully aquatic ancestors, still required periodic contact with moisture to function within normal physiological parameters. The swamp margin was not merely a habitat of opportunity for these animals, it was a physiological requirement. Among the best documented early tetrapods of the Carboniferous is Proterogyrinus, a form reaching body lengths of approximately 1.5 meters, with a broad, flattened skull housing jaws lined with conical teeth, suited to capturing and retaining prey rather than processing it. The skull morphology, low profile, wide and equipped with eyes positioned toward the upper surface, is functionally consistent with an ambush predation strategy executed from a position at or just below the water surface. This configuration, in which the predator's body is submerged while its eyes remain oriented toward the surface or the shallow water column above, minimizes the visual cross-section presented to potential prey approaching from above while maximizing the predator's own field of detection. The ambush strategy itself is energetically conservative. Rather than expending metabolic resources on active pursuit across terrain, an ambush predator invests energy primarily in maintaining position and executing a high-acceleration strike at close range. For an ectothermic animal in a warm Carboniferous swamp, where water temperatures likely ranged between 25 and 32 degrees Celsius based on paleoclimate reconstructions, metabolic rates were sufficient to support the explosive muscular activity requiring the sustained aerobic output that pursuit predation demands. The energy budget of ambush predation in warm, prey-rich, shallow water was, from a physiological standpoint, highly favorable. Prey available to tetrapods in these marginal zones was diverse and, by modern standards, unusually large. Aquatic arthropods, including early members of groups related to modern scorpions, as well as large aquatic insects in larval stages, occupied the water column and substrate. Fish, present in Carboniferous freshwater systems in considerable diversity, moved through the shallower zones in pursuit of their own prey. Smaller tetrapods, juveniles of larger species, and the larvae of amphibious forms all contributed to a prey assemblage that was both abundant and, in many cases, itself dangerous to approach incautiously. The food web at the swamp margin was not organized into simple predator-prey pairs. It was a network of overlapping predatory relationships in which any given organism occupied both predator and prey roles, depending on the size and species of the organism it encountered. The substantial instability of the peat-based wetland floor introduced an additional hazard that operated independently of biological predation. Decomposing plant material in anaerobic conditions produces methane and carbon dioxide as metabolic byproducts of microbial activity. In areas where this decomposition was particularly active, gas accumulation beneath the peat surface could produce sudden localized failures, zones where the structural integrity of the surface layer collapsed under the weight of an animal, creating rapid submersion events in what had appeared to be solid or shallow water terrain. While direct evidence for such events in the Carboniferous fossil record is limited, the physical chemistry of anaerobic peat decomposition is well understood, and the conditions present in Carboniferous coal swamps were consistent with this process, operating at significant scale. Water clarity in these environments was, by most reconstructions extremely low. Suspended organic particles, microbial blooms, and the continuous input of fine sediment from surrounding peat surfaces reduced visibility within the water column to distances of centimeters rather than meters. For organisms navigating beneath the surface, whether predator or prey, visual information was of limited utility beyond immediate proximity. Lateral line systems, present in the aquatic vertebrates of this period and functionally analogous to the pressure-sensing systems of modern fish and aquatic amphibians, provided sensory information about water displacement at distances greater than vision permitted. An approaching animal of sufficient size generated pressure waves detectable at distances of several body lengths, providing both predator and prey with advance information about proximity that vision alone could not supply. The energetic throughput of the swamp margin ecosystem was high. Warm temperatures, abundant organic substrate, and the continuous input of plant material from the surrounding forest maintained bacterial and algal productivity at levels that supported dense invertebrate populations, which in turn sustained the vertebrate predators at the apex of the local food web. Turnover rates, the speed at which energy moved through trophic levels, were accelerated relative to cooler or less productive environments. This productivity was not evenly distributed. It was concentrated along the boundary bones between stream-standing water and emergent vegetation, in areas where organic input was highest and where the physical structure of the habitat provided both concealment and access to multiple prey types simultaneously. The tetrapods that inhabited these margins were not the only vertebrates present. Fish fauna of the Carboniferous included forms reaching lengths of 1 meter or more, some equipped with robust dentition, consistent with hard prey processing, crushing mollusks and heavily armored invertebrates, and others with more generalized predatory morphology. The interaction between large fish and early tetrapods in shared shallow water habitats introduced competitive and predatory dynamics whose details the fossil record preserves only partially. Body size overlap between the two groups in the 1-to-1, 5-meter range suggests that neither consistently dominated the other, and that the outcome of any given encounter was likely determined by local conditions, water depth, proximity to emergent vegetation, and the relative size of the individuals involved. What the swamp margin represented, in aggregate, was an environment in which the probability of a fatal encounter, whether through biological predation, substrate failure, or physiological stress from abrupt transitions between aquatic and terrestrial conditions, was substantially elevated relative to either the open, forest interior or the deeper aquatic zones. The organisms that persisted in this habitat did so through a combination of sensory acuity, behavioral flexibility, and body plans refined by selection pressure operating across millions of generations in precisely these conditions. The margin was dangerous not because it was exceptional, but because danger was its defining and continuous ecological characteristic. Beyond the marginal zones where shallow water met emergent vegetation, the Carboniferous wetland system deepened into a network of permanent swamp, channels, oxbow lakes, and sediment-floored basins that received little direct sunlight and maintained stable water temperatures throughout the year. These were not seasonal water bodies subject to periodic drying. They were persistent features of the lowland landscape, fed by the continuous input of groundwater moving through peat substrates and by surface drainage from the surrounding forest. Their permanence made them centers of biological accumulation. Organisms that required stable aquatic conditions concentrated in these deeper zones, and the food webs that developed within them reflected both the productivity of the surrounding forest system and the specific physical constraints of dark, slow-moving water. The optical properties of these deeper swamp channels differed substantially from the marginal zones. Tannins leaching from decomposing plant material stained the water a deep brown, reducing light penetration to negligible levels within the first half meter of depth. Dissolved oxygen concentrations near the substrate were low, a consequence of microbial respiration consuming available oxygen faster than surface exchange could replenish it. Near the surface, oxygen concentrations were higher, maintained by atmospheric exchange and by the photosynthetic activity of surface algae and floating vegetation. This vertical gradient in dissolved oxygen created a stratified water column in which different organisms occupied different depth ranges according to their respiratory tolerances. The apex vertebrate predators of these permanent swamp systems were large temnospondyl amphibians, a diverse and ecologically dominant group whose members ranged from small, bottom-dwelling forms to massive ambush predators exceeding 2 meters in body length. Temnospondyls were not primitive or transitional animals in any functionally limiting sense. They were highly refined predators whose body plans had been shaped by tens of millions of years of selection in aquatic and semi-aquatic environments. Their skulls were broad, heavily ossified, and equipped with multiple rows of teeth, conical primary teeth lining the jaw margins and smaller palatal teeth on the roof of the mouth, providing secondary grip on captured prey. This dental arrangement is functionally consistent with the capture of large, mobile prey items that required secure retention before processing could occur. Among the larger temnospondyl forms documented from Carboniferous deposits, Cochleosaurus and related genera present skull lengths in the range of 30 to 45 centimeters, implying total body lengths between 1.5 and 2.5 meters based on proportional relationships established from more complete specimens. At these dimensions, and with jaw gape angles consistent with the skull geometry of recovered specimens, prey items up to approximately 40% of the predator's own body length fell within the functional capture range. This encompassed a substantial fraction of the vertebrate fauna sharing the same water bodies, fish of moderate size, smaller tetrapods, and juvenile members of the same or related species. Cannibalism among large temnospondyls is a behavior inferred from both morphological evidence and from taphonomic patterns in fossil assemblages, the spatial relationships between bones in death deposits that suggest one individual consumed another. In modern large aquatic predators, cannibalism functions as a density-dependent behavior, increasing in frequency when prey availability declines relative to predator population density, and as a size-structured interaction in which larger individuals consume smaller ones of the same species. There is no reason to suppose that the ecological logic governing this behavior in modern crocodilians or large salamanders was absent from functionally analogous Carboniferous temnospondyls operating under comparable environmental conditions. The hunting posture most consistent with temnospondyl skull and body morphology is low-profile aquatic ambush, the predator maintaining a stationary or slowly drifting position at or just below the water surface, relying on the concealment provided by dark water and surface vegetation to remain undetected until prey approached within strike range. The strike itself would have been a rapid, lateral sweep of the jaws combined with a forward lunge of the body, powered by the axial musculature of the trunk. In modern ambush-adapted aquatic predators of comparable body plan, crocodilians being the closest functional analog, strike initiation to jaw closure occurs within fractions of a second, generating acceleration forces that prey animals in the immediate vicinity have insufficient reaction time to avoid. Territorial behavior in large aquatic predators is typically organized around resource control, access to productive feeding areas, basing sites where thermoregulation is possible, and zones that provide shelter from larger conspecifics. In permanent swamp channels of the Carboniferous, the distribution of these resources was determined by the physical structure of the water body itself. Channel bends, where current slowed and organic material accumulated, concentrated prey and provided natural ambush positions. The edges of submerged peat banks, where the substrate created defined depth transitions, offered cover and structural reference points for an animal maintaining territorial position. Encounters between individuals of comparable size at these resource-concentrated locations would have resulted in direct physical confrontation, jaw displays, lateral body presentations, and, where size differences were insufficient to resolve the interaction through signaling alone, contact aggression. The sensory systems available to temnospondyls in the low visibility conditions of the Black Swamp were necessarily weighted toward non-visual modalities. Lateral line canals, grooves and pits on the skull surface that housed mechanoreceptive sensory organs are preserved in the dermal bone of multiple temnospondyle genera, indicating that pressure wave detection remained a primary sensory channel for these animals in turbid water. The geometry of lateral line canal distribution on the skull surface provides information about the directional sensitivity of the system. Canals arranged along the jaw margins and across the snout would have been particularly sensitive to the pressure disturbances generated by swimming prey at close range, providing the predator with spatial information sufficient to orient a strike in the absence of useful visual input. Below the temnospondyls in the size hierarchy of the swamp system, a secondary layer of predators occupied the middle trophic positions. Large aquatic invertebrates, including predatory eurypterids in some Carboniferous water bodies, though their diversity was declining relative to earlier periods, competed with smaller tetrapods and large fish for the intermediate prey base of aquatic insects, worms, and small vertebrates. The interaction between these middle-tier predators and the apex temnospondyls introduced a set of behavioral constraints on foraging. Middle-tier predators operating in areas occupied by large temnospondyls faced predation risk that influenced their habitat use, activity timing, and the prey sizes they were willing to pursue before retreating to cover. The permanent swamp channels also accumulated organic material from the surrounding forest at rates that sustained high microbial productivity at the sediment-water interface. This benthic productivity supported a community of bottom-dwelling invertebrates. Early oligochaete-grade worms, aquatic insect larvae, and small crustaceans that formed the base of the aquatic food web. Energy entered this system from above through the continuous rain of organic particles settling through the water column and was processed upward through successive trophic levels until it reached the large temnospondyl predators at the apex. The efficiency of this energy transfer, the fraction of energy at each trophic level that successfully reached the next, was governed by the same thermodynamic constraints that apply to all food webs, meaning that the large predators at the top required a disproportionately productive base to sustain their population densities. What these swamp systems represented ecologically was a stable, high-productivity environment in which size-structured predation organized the biological community from the bottom up and the top down simultaneously. Productivity from microbial and invertebrate sources supported the prey base. The prey base supported intermediate predators. Intermediate predators supported apex forms whose size, sensory capability, and behavioral repertoire had been refined across millions of years of selection in precisely these conditions. The black swamps of the Carboniferous were not chaotic environments. They were tightly organized biological systems in which every organism occupied a position defined by its size, physiology, and the predatory relationships that connected it to every other organism in the same water body. The atmospheric conditions of the late Carboniferous period were not a background detail of the ecosystem, they were its governing parameter. Every aspect of biological scaling, from the maximum body size achievable by trachea-dependent arthropods to the fire ecology of the forest itself, was directly constrained or enabled by the concentration of oxygen in the air. Understanding why that concentration reached the levels it did requires tracing a chain of causation that begins with the biochemistry of plant cell walls and extends outward to encompass the global carbon cycle, the weathering of continental rock, and the tectonic configuration of the land masses themselves. Oxygen began accumulating in Earth's atmosphere in significant quantities approximately 2.4 billion years ago, during the Great Oxidation Event, as photosynthetic bacteria released oxygen as a metabolic byproduct faster than geological sinks could absorb it. For most of the subsequent billions of years, atmospheric oxygen remained well below the concentrations of the Carboniferous, held in check by the balance between photosynthetic production and oxidative consumption through respiration, weathering, and volcanic outgassing. The shift that produced the Carboniferous oxygen spike was not a change in photosynthesis itself. It was a change in what happened to the organic carbon that photosynthesis produced. The critical factor was lignin. Vascular plants evolved the capacity to synthesize lignin, a complex, aromatic polymer that provides structural rigidity to woody tissue. During the Devonian period, approximately 400 million years ago, lignin is among the most chemically resistant biological molecules produced by living organisms. Its decomposition requires specialized enzymatic systems, primarily the oxidative enzymes produced by certain fungal lineages. During the early evolution of lignin-producing plants, the fungal communities capable of efficiently breaking down this compound had not yet diversified to match the scale of lignin production. The result was a prolonged period, spanning much of the Carboniferous, during which dead woody plant material accumulated in sedimentary basins faster than it decomposed. This accumulation had a direct atmospheric consequence. Photosynthesis converts carbon dioxide and water into organic carbon and oxygen. When the organic carbon produced by this process is subsequently decomposed by respiration or oxidation, the oxygen consumed in that process approximately equals the oxygen originally released. The net atmospheric oxygen contribution of photosynthesis under normal conditions is therefore close to zero. But when organic carbon is buried in sediment rather than decomposed, the oxygen released during its photosynthesis is not recaptured. It remains in the atmosphere. The massive burial of lignin-rich plant material in Carboniferous coal basins therefore represented a sustained, large-scale injection of oxygen into the atmosphere that persisted for tens of millions of years. Geochemical modeling of this process, using isotopic records preserved in marine sediments and carbonate rocks, produces oxygen concentration estimates for the late Carboniferous that consistently fall in the range of 30 to 35%. These models incorporate inputs from carbon isotope ratios, which reflect the relative balance between organic carbon burial and oxidative return, and from sulfur isotope ratios, which track the activity of sulfate-reducing bacteria in marine sediments and provide an independent constraint on oxygen levels. The convergence of multiple independent geochemical proxies on similar oxygen concentration values increases confidence in the reconstruction, though uncertainty ranges of several percentage points remain inherent to the methodology. The physical consequences of 35% atmospheric oxygen extended beyond arthropod bodily size into the fire ecology of the forest. Combustion requires oxygen, and the ignition threshold and burn intensity of plant material both increase with atmospheric oxygen concentration. Experimental work has established that plant material ignites and sustains combustion more readily at oxygen concentrations above approximately 25%, with fire spread rates increasing non-linearly above this threshold. Charcoal, fossil charcoal, termed fusain, is present in Carboniferous coal deposits at frequencies and in quantities consistent with recurring fire events across the forest. Landscape. Lightning strikes in a forest where leaf litter, fallen logs, and standing dry vegetation ignited at lower temperatures and burned more intensely than in a modern atmosphere would have produced fires whose spatial extent and duration exceeded those typical of present-day forest fire regimes. These fires were not logically catastrophic in the sense of permanently destroying the forest. The rapid regrowth capacity of lycopod trees, which could reach full height within years rather than decades, and the high moisture content of the Swamp-dominated lowlands provided both recovery mechanisms and natural fire breaks. Fire events likely operated as episodic disturbances that created clearings, recycled nutrients from accumulated organic material into the soil and water, and maintained a landscape mosaic of vegetation at different successional stages. The charcoal deposited by these fires contributed to the carbon burial record, adding another pathway through which carbon was sequestered in forms resistant to rapid oxidative return. The elevated oxygen atmosphere also influenced the physiology of vertebrates present in the Carboniferous, though the relationship is less direct than for trachea-dependent arthropods. Vertebrate respiration operates through lungs, organs that actively ventilate and where oxygen uptake is mediated by hemoglobin in the blood. The efficiency of this system is less directly dependent on atmospheric oxygen concentration across the range of variation relevant to the Carboniferous, meaning that vertebrate body size was not elevated by the high oxygen atmosphere in the same mechanistic way that arthropod body size was. However, elevated atmospheric oxygen does increase the partial pressure of oxygen in inhaled air, potentially supporting higher sustained aerobic metabolic rates and influencing the upper limits of activity intensity in lung-breathing vertebrates. The carbon dioxide concentration of the Carboniferous atmosphere was, as a direct consequence of the same organic carbon burial process that elevated oxygen substantially lower than in preceding periods. Carbon dioxide had been drawn down from concentrations estimated at several thousand parts per million during the early Paleozoic to values approaching or possibly falling below modern pre-industrial concentrations of approximately 280 parts per million during the late Carboniferous glacial intervals. This drawdown had global climatic consequences. Carbon dioxide is a primary greenhouse gas, and its reduction contributed to a long-term cooling trend that produced glaciation at the southern pole, centered on the Gondwana supercontinent, and introduced a degree of climatic variability that the consistently warm, humid conditions of the earlier Carboniferous had not exhibited. The forest was, in this sense, actively modifying the planetary conditions under which it existed. By burying carbon and releasing oxygen, it was simultaneously cooling the climate, reducing the greenhouse effect, and elevating the atmospheric oxygen that enabled its largest arthropod inhabitants. The system contained within it the parameters of its own transformation. As carbon dioxide concentrations fell and glacial cycles intensified, the stable, warm, humid conditions that had sustained continuous lycopod forest across the equatorial lowlands became increasingly interrupted. The atmospheric chemistry that the forest had created was, over geological timescales, undermining the climatic stability on which the forest depended. A feedback relationship whose consequences would unfold across the millions of years that followed the Carboniferous peak. Sometime during the Middle Carboniferous, approximately 312 million years ago, a lineage of small tetrapods accomplished something that no vertebrate had achieved before. They reproduced on dry land the egg they laid, or, in some early forms, retained internally through an equivalent physiological innovation. Contained within its membranes a self-enclosed aquatic environment, the amnion, a fluid-filled sac surrounding the embryo that replicated the chemical and physical conditions of water without requiring immersion in an external water body. This single reproductive innovation dissolved the biological tether that had bound every previous vertebrate lineage to standing water for the most critical phase of its life cycle. Its consequences, ramifying outward through evolutionary time, would eventually produce every reptile, bird, and mammal that has existed on Earth. The amniote egg is not a simple structure. It consists of several distinct membranes, the amnion surrounding the embryo directly, the chorion mediating gas exchange with the external environment, and the allantois storing metabolic waste products, all enclosed within a shell that in early amniotes was likely leathery rather than calcified, as in modern reptile eggs. The functional integration of these membranes allowed the embryo to complete its development in a controlled internal environment. Regardless of external moisture availability, while the shell regulated water loss to a degree sufficient to prevent desiccation across the incubation period. The evolutionary steps leading to this arrangement are not fully preserved in the fossil record, but the comparative anatomy of modern amniotes and their living relatives allows a functional reconstruction of the likely developmental sequence. The earliest definitively identified amniotes appear in the fossil record from sites in Nova Scotia, specifically the famous Joggins Formation, a Carboniferous coastal cliff section that preserves an extraordinary assemblage of early tetrapod material in the interior cavities of hollow, lycopod tree stumps. Hylonomus lielli, recovered from these deposits and dated to approximately 312 million years ago, is among the earliest amniotes currently recognized, with a body length of approximately 20 centimeters and a skeletal morphology indicating a fully terrestrial lifestyle. Its limb proportions, vertebral structure, and skull geometry all suggest an animal capable of sustained locomotion on land, with no morphological indicators of the aquatic adaptations: flattened tail, lateral line canals, reduced limb robustness that characterized more water-dependent contemporaries. The ecological context of Hylonomus and its close relatives is informative. These animals were small, body lengths in the 15 to 25 centimeter range, and their jaw morphology and tooth structure indicate a diet of small invertebrates, most likely insects and other arthropods, present on the forest floor. The forest interior, away from the swamp margins, offered a prey base that earlier, water-dependent tetrapods could not access without risking desiccation. Arthropods were abundant at ground level, present year-round in the warm Carboniferous climate, and ranged in size from millimeter-scale individuals to form several centimeters in length, all within the prey size range of a 20-centimeter predator. The amniote condition, by freeing these small predators from the requirement to remain near standing water, opened the entire forest interior as accessible foraging habitat. The structural features that supported full terrestriality in early amniotes extended beyond reproductive biology. Skin permeability to water loss was reduced relative to earlier tetrapods, limiting the rate of desiccation during periods away from moisture. Kidney function was modified toward greater water conservation, producing more concentrated nitrogenous waste. Limb musculature and joint geometry were refined to support sustained locomotion on relatively dry, firm substrates. The compressed leaf litter and exposed root systems of the forest floor, rather than the soft, unstable sediment of swamp margins. Each of these modifications reinforced the others, creating a suite of integrated adaptations that collectively permitted these animals to operate in environments physiologically inaccessible to their amphibian contemporaries. The forest interior that early amniotes entered was not an unoccupied ecological space. Large arthropods, millipede-grade detritivores, ground-level arachnids, and a diversity of cockroach-like insects were already established as the dominant fauna of the deep forest floor. Early amniotes inserted themselves into this community as small, mobile, visually oriented predators, occupying a predatory niche that the arthropod fauna had not previously faced from a vertebrate source. Their visual systems, forward-facing eyes in at least some early forms, providing binocular overlap useful for distance estimation during prey capture, represented a sensory capability complementary to the vibration and chemoreception systems that arthropods used for environmental awareness. The hollow lycopod stumps that preserved the Joggins Formation amniotes are themselves ecologically informative. These stumps formed natural pitfall traps. Animals that fell into them could not easily escape the smooth interior walls, and the assemblages recovered from multiple stumps include both the amniotes themselves and representatives of the invertebrate community on which they likely fed. The co-occurrence of early amniotes with large cockroach-like insects, small arachnids, and millipede fragments in the same depositional context provides a direct, spatially constrained record of the ecological community within which these earliest fully terrestrial vertebrates lived and hunted. The diversification of amniotes, following their initial appearance, proceeded along multiple ecological trajectories. Within a relatively short geological interval, tens of millions of years rather than hundreds, the amniote lineage split into the two major groups, whose descendants persist today: the sobsids, ancestral to modern reptiles and birds, and the synapsids, ancestral to modern mammals. This divergence, detectable in the fossil record through differences in skull fenestration patterns and other skeletal features, established two parallel evolutionary trajectories that would dominate terrestrial vertebrate evolution for the remainder of Earth's history. The Carboniferous forest in this context was the environment in which the founding lineage of both trajectories first established itself as a viable ecological entity. The significance of the amniote transition is difficult to overstate in terms of its long-term biological consequences, but it is equally important to understand it as a product of specific Carboniferous conditions rather than as an inevitable developmental endpoint. The particular combination of a forest interior rich in arthropod prey, an elevated oxygen atmosphere that supported dense invertebrate populations, a warm and stable climate that permitted year-round terrestrial activity by small ectotherms, and the specific evolutionary starting point represented by the semi-terrestrial tetrapods of the swamp margins, all of these factors converged to create the selective environment in which the amniote condition provided sufficient advantage to establish and persist. The transition did not occur abruptly, and its early stages are not cleanly preserved in the fossil record. The gap between the last clearly non-amniote tetrapods and the first definitively identified amniotes encompasses a period during which intermediate forms, animals in the process of acquiring the full suite of amniote adaptations, lived and died without leaving recoverable remains. What the fossil record provides are endpoints: the water-dependent tetrapods of the swamp margin on one side, and the fully terrestrial amniotes of the forest interior on the other. The pathway connecting them must be inferred from the comparative anatomy of their descendants and from the physical logic of the selective pressures operating in the Carboniferous environment. That inference, though necessarily incomplete, points consistently toward the forest interior, its prey resources, its stable climate, and its vast unoccupied terrestrial space. As the ecological engine that drove one of the most consequential transitions in the history of vertebrate life. As the Carboniferous sun descended below the horizon, the thermal regime of the forest underwent a measurable and consequential shift. During daylight hours, the upper canopy of lycopod trees absorbed solar radiation across its photosynthetically active surface, converting light energy into chemical bonds while releasing water vapor through transpiration. This process maintained canopy temperatures several degrees above ambient air temperature and drove the convective air circulation that characterized the daytime forest interior. With the removal of solar input at nightfall, this thermal engine ceased. Canopy temperatures dropped toward ambient within the first hour of darkness, and the convective circulation that had moved warm, humid air upward through the forest structure stalled and reversed, allowing cooler air to settle toward the forest floor. The temperature differential between day and night in the equatorial Carboniferous was smaller than would be expected at higher latitudes, constrained by the high moisture content of the atmosphere and the thermal buffering effect of the extensive water bodies distributed across the lowland landscape. Paleoclimate reconstructions suggest diurnal temperature ranges in the equatorial forest zone of perhaps 5 to 8 degrees Celsius, modest by the standards of modern continental interiors, but sufficient to produce meaningful changes in the activity levels of ectothermic organisms, whose metabolic rates are directly coupled to environmental temperature. For the large arthropods that dominated the forest floor and aerial zones, the onset of darkness and the associated temperature decrease had direct physiological consequences. Arthropod nervous system conduction velocity, muscle contraction speed, and overall locomotor performance are temperature dependent. A drop of 5 degrees Celsius reduces these functional parameters measurably, shifting large arthropods toward reduced activity and slower response times. This shift did not eliminate arthropod activity at night. The thermal buffering of the humid forest interior prevented temperatures from falling to levels that would induce torpor in most forms. But it altered the competitive and predatory dynamics of the nocturnal environment in ways that favored organisms with temperature-independent activity regulation. The early tetrapods and amniotes of the Carboniferous were, like all vertebrates of this period, ectothermic. Their body temperatures tracked environmental temperature rather than being internally regulated. However, the thermal inertia of a larger body mass means that a 1.5-meter temnospondyle cools more slowly than a 5-centimeter arthropod after solar input ceases. For the first hours of darkness, larger ectotherms retained body temperatures closer to their daytime operational range than did smaller ones, potentially preserving a functional performance advantage during the transitional period between full daylight activity and the cooler, stable temperature regime of midnight. This size-dependent thermal inertia may have structured the timing of predatory activity across the dusk transition period. The acoustic environment of the Carboniferous forest at night was fundamentally different from that of modern forests in one significant respect: the absence of vertebrate vocalizers. In modern tropical forests, the nocturnal soundscape is dominated by frogs, insects, and birds. Vertebrate and invertebrate vocalizers using sound for mate attraction, territorial advertisement, and alarm signaling. Carboniferous frogs did not yet exist. The earliest frog lineage tetrapods would not appear until the Triassic. The acoustic signaling systems that characterize modern amphibian communities had not yet evolved in any lineage present in the Carboniferous forest. The nocturnal soundscape was therefore composed entirely of invertebrate-generated sound. The mechanical stridulation, wing movement, and substrate vibration produced by the abundant arthropod fauna. Large griffinflies, whose wing venation and body mass suggest active flight during daylight hours when thermal updrafts and visual prey detections supported aerial predation, likely reduced flight activity during darkness. The compound eye morphology of griffinflies, large but not specifically adapted for low light sensitivity in the manner of modern nocturnal insects, indicates that visual prey detection was a primary hunting mechanism, one that became progressively less effective as light levels declined. Griffinfly activity at night was therefore probably confined to periods of sufficient ambient light from bioluminescence or moonlight, though the latter source was substantially different in the Carboniferous. The moon was closer to Earth at this period, producing higher tidal forces and a somewhat larger apparent disk, with implications for the intensity of moonlit nights that are difficult to quantify precisely. The ground-level arthropod community, by contrast, included forms whose sensory systems were less dependent on vision and therefore less constrained by darkness. Large myriapods bards navigated primarily through mechanoreception and chemoreception, detecting substrate vibration and chemical gradients rather than forming optical images of their environment. Arthropleura, moving through the forest floor on its dozens of leg pairs, processed the environment through contact and chemical sensing, systems that functioned as effectively in darkness as in daylight. Arachnid-grade predators present in the Carboniferous likewise relied on vibration-sensitive mechanoreceptors, the slit sensilla and lyre organs, distributed across their appendages, that detected prey movement through subtransmitted vibration rather than visual detection. The swamp water bodies of the forest underwent their own nighttime transition. During daylight hours, Photosynthetic activity by surface algae and aquatic plants produced oxygen that partially offset the oxygen deficit in the water column created by microbial respiration at the sediment surface. At night, photosynthesis ceased while microbial and animal respiration continued, causing dissolved oxygen concentrations in shallower, poorly mixed water bodies to decline toward the sediment surface. For the aquatic vertebrates occupying these systems, temnospondyls and fish, this nocturnal oxygen decline potentially drove a behavioral response, movement toward the surface or toward better oxygenated zones, increasing the concentration of predators and prey in the upper water column during the hours of darkness. The forest canopy at night presented a structural environment that differed from its daytime configuration, primarily in terms of the organisms active within it. The upper surfaces of lycopod leaves and branches, warmed during the day by solar radiation, cooled toward ambient temperature after sunset, reducing their attractiveness as basking surfaces for any organisms that might have used them for thermoregulation. The structural complexity of the canopy, its interlocking branches, pendant spore-bearing structures, and layered leaf arrangements remained unchanged, providing the same three-dimensional habitat architecture that daytime canopy fauna had exploited, now occupied by a different community of organisms whose sensory and physiological profiles suited the altered conditions. Bioluminescence in the Carboniferous cannot be directly confirmed from the fossil record, as the biochemical systems responsible leave no preservable trace. However, the evolutionary origins of bioluminescence in multiple independent fungal and invertebrate lineages suggest that the biochemical precursors were present in Carboniferous organisms, and that some degree of biological light production occurred within the forest, particularly associated with decaying wood, a substrate that supports bioluminescent fungal activity in modern forests globally. The contribution of this light source to the nocturnal visual environment of the forest floor was likely minimal in terms of illumination intensity, but its presence would have represented a source of biological information, a signal of decay, moisture, and microbial activity for any organism capable of detecting and interpreting it. The Carboniferous night was not a cessation of ecological activity. It was a reorganization of that activity around a different set of sensory modalities, thermal constraints, and resource distributions. The organisms that navigated it successfully did so through sensory systems calibrate to low light or light-independent environmental information, body plans that retained sufficient thermal inertia to maintain metabolic function through the temperature decline, and behavioral flexibility sufficient to exploit the altered distribution of prey and competitors that darkness produced. The forest continued its biological processes without interruption, metabolizing, growing, hunting, and decomposing across the full diurnal cycle, driven by energy flows and chemical gradients that darkness modified but did not arrest. Kawinyu, you said, continue but max 7,000 characters. Resources in the Carboniferous forest were not uniformly distributed across the landscape. Productive foraging zones, thermally favorable basking sites, stable water bodies with reliable prey concentrations, and structurally complex refugia offering protection from larger predators were all spatially constrained features of the environment. Their uneven distribution meant that access to them was finite, and that multiple organisms with overlapping ecological requirements would inevitably compete for the same locations. This competition, operating simultaneously at the level of individuals, species, and entire ecological guilds, was not incidental to the functioning of the Carboniferous ecosystem. It was one of its primary organizing forces, driving behavioral specialization, morphological divergence, and the escalating arms race dynamics that characterized predator-prey and competitor-competitor relationships across tens of millions of years. Among the large arthropods of the forest floor, competitive interactions were structured primarily by body size. In systems where individuals of the same or related species compete for the same resources, size asymmetry typically determines the outcome of direct encounters. Larger individuals displace smaller ones from preferred locations without necessarily engaging in prolonged physical conflict. The energetic cost of displacement behavior is lower than the cost of sustained fighting, and the information content of a size differential, communicated through direct visual assessment or through substrate vibration patterns during locomotion, is sufficient for smaller individuals to assess the outcome of a potential encounter and withdraw before contact occurs. This size-structured displacement behavior concentrates the highest quality resources in the largest individuals while distributing smaller or lower quality resources among progressively smaller competitors. For Arthropleura, the largest individuals, those approaching 2.5 meters in length, occupied a size class with no potential arthropod competitors of comparable dimensions. Their movement through the floor effectively displaced all smaller myriapods and ground-level arthropods from the immediate vicinity, not through active aggression, but through the mechanical disturbance of their passage and the chemical signals deposited in trackways. Smaller Arthropleura individuals, juveniles of the same species or adults of smaller related species, occupied the same forest floor habitat but in practice accessed different spatial zones. The margins of fallen logs, the spaces between root masses, and the narrower corridors between standing tree trunks where larger individuals could not easily maneuver. The aerial zone above the canopy exhibited competitive dynamics of a different character. Griffinfly scale predators, occupying overlapping foraging ranges, would have encountered one another, with a frequency determined by their population, density and the spatial extent of their foraging flights. In modern large territorial predatory insects, including some large dragonfly species, males actively defend airspace territories over productive foraging areas, engaging in pursuit and contact behavior toward intruding conspecifics. The wing morphology of griffinflies, robust with venation patterns indicating capacity for rapid directional changes, is consistent with the aerial maneuverability that territorial flight behavior requires. The energetic investment in territorial defense is justified when the defended resource, in this case airspace over concentrated prey populations, provides a sufficiently higher foraging return than undefended areas. The interaction between large arthropods and the early tetrapod vertebrates of the swamp margins introduced an intergroup competitive dimension whose terms were defined by the very different body plans and sensory systems of the two parties. A temnospondyle of 1.5 meters body length and a large myriapod of comparable or greater length occupied partially overlapping ecological space at the swamp margin. Both were present in the same physical zone, both processed organic material or prey at the same spatial scale, and both required access to the stable, moisture-rich conditions that the swamp margin provided. Direct predatory interaction between these two groups is possible. A large temnospondyle encountering a juvenile Arthropleura in shallow water would likely have attempted predation, but the primary competitive relationship was probably indirect, organized around access to the same productive marginal zones rather than direct physical conflict. Early amniotes, operating in the drier forest interior at body sizes an order of magnitude smaller than the apex predators of the swamp system, competed primarily within their own size class and with the arthropod fauna of the forest floor. Competition between a 20-centimeter amniote and the cockroach-grade insects of comparable body length was organized around access to invertebrate prey, the same arthropods that both groups consumed. The amniote's advantage in this interaction derived from its locomotor speed, its binocular visual system capable of precise distance estimation, and its ability to pursue prey across substrates and into spaces that the pursuing arthropod predators of the same zone, arachnids and predatory myriapods, navigated less efficiently. The arthropod fauna's advantage derived from numerical abundance, chemical detection capability, and the exoskeletal protection that made smaller arthropods difficult to consume without specific handling behaviors. The competition between early synapsid and sauropsid amniotes, the two major lineages into which the amniote radiation divided, is detectable in the fossil record through patterns of ecological divergence that suggest resource partitioning rather than direct competitive exclusion. Early synapsids tended towards slightly larger body sizes and more robust dentition in some lineages, while early sauropsids showed greater diversity of body form at smaller size classes. This divergence, if interpreted as a response to competitive pressure between the two groups, suggests that ecological character displacement, the evolutionary divergence of competing species toward different resource use patterns, was operating within the early amniote community during the Carboniferous. The mechanism is the same one that structures competitive communities, modern ecosystems. Direct competition for identical resources is energetically costly, and lineages that shift their resource use away from areas of maximum overlap gain a competitive advantage. The swamp water bodies were theaters of territorial competition, organized around the specific geometry of productive aquatic habitats. Channel bends, submerged log structures, and the edges of emergent vegetation stands all concentrated prey and provided structural cover, features that large, temnospondyls would have defended against conspecific intrusion, with behaviors analogous to those observed in modern crocodilians. Crocodilian territorial behavior involves both acoustic signaling, low-frequency vibrations transmitted through water, and direct physical confrontation in which jaw-to-jaw contact and body-rolling behavior determine dominance. The skull morphology of large temnospondyls, with its robust construction and evidence of bite force sufficient to cause bone damage, is consistent with intraspecific contact aggression of this type, and healed bite marks on temnospondyle bones from multiple Carboniferous sites provide direct fossil evidence that such interactions occurred and that individuals survived them. The ecological pressure generated by competition at multiple levels, between individuals of the same species, between species within the same guild, and between entire ecological groups organized around different body plans and physiological systems, was a continuous driver of evolutionary change across the Carboniferous. Lineages that developed more efficient foraging strategies, more effective competitive signaling, or morphological specializations that reduced direct overlap with dominant competitors gained reproductive advantages that accumulated across generations. The result was not a stable community in static equilibrium, but a continuously shifting assemblage in which the relative competitive positions of different lineages changed as evolutionary responses to competitive pressure propagated through the ecosystem. The forest was not merely a backdrop against which competition occurred. It was itself a product of that competition, its physical structure shaped by the organisms that inhabited it, and in turn shaping the competitive dynamics that drove their evolution. You said, continue, but max 7,000 characters. The Carboniferous forest did not exist in isolation from the broader Earth system. Its biological processes, photosynthesis, organic carbon production, partial decomposition, and sedimentary burial, connected directly to the global cycles of carbon, oxygen, and climate that governed conditions across the entire planet. The scale of this connection was not trivial. Over the approximately 60 million years of the Carboniferous period, the forests of the equatorial lowlands buried organic carbon in quantities sufficient to measurably alter the composition of the atmosphere, shift global temperatures, and initiate glacial cycles at the poles. The coal deposits that geological surveys have mapped across Europe, North America, and Asia represent the compressed, chemically altered remnants of this buried biomass, a physical record of a biological process that reshaped Earth's chemistry on a planetary scale. The mechanism connecting forest productivity to atmospheric change operated through the carbon cycle. Atmospheric carbon dioxide enters plant tissue through photosynthesis, where it is incorporated into organic molecules, cellulose, lignin, proteins, and lipids that constitute the structural and metabolic components of the plant body. When a plant dies and its organic material is decomposed by microbial and fungal activity, that carbon is returned to the atmosphere as carbon dioxide, completing the cycle with no net change in atmospheric composition. The critical deviation from this cycle in the Carboniferous was the inhibition of decomposition. Lignin, constituting a substantial fraction of the dry mass of lycopod trees and other woody Carboniferous plants, resisted microbial breakdown to a degree that allowed large quantities of organic carbon in a sedimentary burial before decomposition could return it to the atmosphere. The volume of carbon sequestered through this process across the Carboniferous was enormous by any measure. Current estimates, derived from the known extent and thickness of Carboniferous coal seams, combined with models of the original organic carbon content of the peat precursors, suggest that the coal-forming forests buried carbon at rates that reduced atmospheric carbon dioxide concentrations from values of several thousand parts per million in the early Paleozoic to values approaching or falling below 300 parts per million during the late Carboniferous. This reduction, a drawdown of roughly an order of magnitude in the primary atmospheric greenhouse gas, had direct consequences for global surface temperatures through the reduced greenhouse effect. The climatic response to this carbon drawdown was not immediate in human timescales, but it was geologically rapid. As carbon dioxide concentrations fell through the Carboniferous, global mean temperatures declined correspondingly. The southern polar region, occupied at this time by the Gondwana supercontinent, a landmass that included what are now Antarctica, South America, Africa, India, and Australia, developed continental ice sheets of significant extent. Glacial and interglacial cycles, driven by orbital variations in Earth's relationship to the Sun, and amplified by the reduced greenhouse buffering capacity of a low carbon dioxide atmosphere, began to impose periodic climate oscillations on the equatorial forest system. These oscillations, alternating between slightly warmer and wetter conditions during interglacials and cooler, drier conditions during glacial maxima, introduced a degree of climatic variability that the consistently stable conditions of the earlier Carboniferous had not included. The forest's influence on atmospheric oxygen operated in parallel with its drawdown of carbon dioxide. As previously established, the burial of organic carbon without oxidative decomposition left the oxygen produced during photosynthesis unreturned to the atmosphere, driving oxygen concentrations progressively upward through the Carboniferous. The two atmospheric changes, rising oxygen and falling carbon dioxide, were not independent processes. They were opposite sides of the same biochemical accounting. Every carbon atom buried in sediment represented one molecule of carbon dioxide removed from the atmosphere and a corresponding quantity of oxygen left unreturned in it. The forest was simultaneously depleting one atmospheric component and enriching another, with consequences for both climate and biology operating across overlapping but distinct timescales. The global carbon cycle also operated through the ocean system, which interacted with the terrestrial carbon burial process through the exchange of carbon dioxide across the air-sea interface. As atmospheric carbon dioxide declined, the ocean equilibrated toward lower dissolved carbon dioxide concentrations, reducing the acidity of surface seawater and altering the carbonate chemistry of marine environments. These changes propagated through marine ecosystems, affecting organisms that built calcium carbonate shells and skeletons, a group encompassing a substantial fraction of Carboniferous marine biodiversity. The terrestrial forest, through its alteration of atmospheric chemistry, was therefore influencing ecological conditions in ocean systems thousands of kilometers from the nearest tree. Weathering of continental silicate rocks provided a feedback mechanism that partially regulated the carbon drawdown driven by the forest. Silicate weathering, The chemical reaction between rainwater, carbon dioxide, and mineral surfaces in exposed rock consumes atmospheric carbon dioxide and delivers calcium and bicarbonate ions to river systems, eventually reaching the ocean where they are incorporated into carbonate sediments. The rate of silicate weathering increases with temperature, atmospheric carbon dioxide concentration, and the availability of fresh rock surfaces exposed by tectonic uplift and erosion. As Carboniferous forests colonized previously bare or sparsely vegetated continental surfaces, their root systems physically fractured rock substrates, and their root-associated fungi produced organic acids that accelerated chemical weathering. The forest therefore simultaneously buried carbon through organic matter accumulation and consumed additional carbon through enhanced weathering, two reinforcing pathways of carbon removal from the atmosphere operating across the same landscape. The tectonic configuration of the Carboniferous continents influenced the distribution and extent of coal-forming forests in ways that interacted with global climate. The assembly of Pangaea, the supercontinent formed by the collision of La Russia and Gondwana during the late Carboniferous, created mountain ranges whose weathering contributed to carbon drawdown and whose rain-shadow effects produced regional aridity patterns that limited forest extent in some areas while concentrating it in others. The closing of the seaway between the colliding continents altered ocean circulation patterns, affecting heat distribution across the global ocean and contributing to the cooling trend that produced southern glaciation. The forest did not operate in a tectonically static environment. It was embedded in a planetary system undergoing significant structural reorganization, and the interaction between biological and geological processes determined the trajectory of atmospheric and climatic change across the period. The coal seams that the Carboniferous forest produced have structured human industrial history in ways whose scale is difficult to overstate. The carbon buried by lycopod trees and their associated plant communities 300 million years ago fueled the Industrial Revolution, powered the expansion of global manufacturing and transportation networks, and contributed the majority of the carbon dioxide increase measured in Earth's atmosphere since the mid-18th century. The atmospheric consequences of Carboniferous carbon burial, the oxygen elevation, the carbon dioxide drawdown, the glacial cycles operated across millions of years. The reversal of that burial, through the combustion of coal and other fossil fuels, has introduced comparable quantities of carbon dioxide into the atmosphere across a time frame measured in centuries. The forest that changed the planet during the Carboniferous left behind, in its compressed remains, the chemical potential for a second planetary transformation, one whose consequences are distributed not across geological time, but across human generations. The stability that had characterized the Carboniferous lowland forest for tens of millions of years was not permanent. Beginning approximately 307 million years ago, at the transition between the Pennsylvanian and the earliest Permian, the climatic conditions that had sustained continuous lycopod forest across the equatorial basins began to shift in ways that were gradual in geological terms but consequential in biological ones. The changes did not arrive as sudden catastrophe. They arrived as incremental alterations in the frequency and intensity of dry seasons, as subtle reductions in the permanence of swamp water bodies, and as the slow fragmentation of what had been a largely continuous forest landscape into an increasingly patchy mosaic of wet and dry habitat. For organisms whose body plans and physiological requirements had been refined over millions of years under stable conditions, these incremental changes represented pressures for which their evolutionary histories had not prepared them. The glacial-interglacial cycles that intensified through the late Carboniferous and into the early Permian were the primary driver of this habitat fragmentation. During glacial maxima, when ice sheets expanded across the Gondwana supercontinent and global temperatures declined, the equatorial climate dried measurably. Precipitation patterns shifted. reducing the reliable moisture input that had maintained permanent swamp conditions across the lowland basins. During interglacials, conditions temporarily recovered toward the warm and wet regimes of the earlier Carboniferous, but the recovery was incomplete. Each successive cycle left the forest slightly more fragmented, the water bodies slightly less permanent, and the dry intervals slightly longer than the previous one. This ratcheting pattern of incremental habitat degradation is documented in the sedimentary record through the alternating coal and clastic sediment layers preserved in Carboniferous Permian boundary sequences across Europe and North America. The giant lycopod trees, Lepidodendron, Sigillaria, and their close relatives were among the organisms least equipped to respond to these shifting conditions. Their reproductive biology was deeply constrained by water availability. Spore germination required standing water, and the gametophyte phase of their life cycle, the small sexually reproductive stage that preceded the development of the large sporophyte tree, was particularly vulnerable to desiccation. In a landscape where standing water was present year-round and across large continuous areas, this reproductive requirement was easily met. In a landscape where water bodies were smaller, more isolated, and subject to seasonal drying, the spatial and temporal windows within which successful spore germination could occur were progressively reduced. Lycopod recruitment, the establishment of new individuals to replace those that died, declined as these windows narrowed. The consequence of reduced recruitment was not immediate forest loss. Mature lycopod trees, once established, were structurally robust and capable of persisting for years under conditions that prevented new establishment. The forest could therefore maintain its physical structure and ecological function for a period after reproductive success had declined below replacement rates. But a forest in which established individuals were dying at the normal rate while new recruitment was failing was a forest in slow demographic collapse, its age structure shifting toward older individuals, its canopy becoming less continuous as gaps opened faster than they were filled, and its interior microclimate changing as increased light penetration and reduced transpiration altered the thermal and humidity conditions of the forest floor. The organisms most severely affected by lycopod forest decline were those whose ecological requirements were most specifically calibrated to the conditions that forest created. Giant arthropods, Arthropleura, and the broader community of large myriapods, large cockroach-like insects, and ground-level detritivores depended on the forest floor environment for their primary resources. The accumulation of organic material that sustained the detritivore community required continuous input from the canopy above. As the canopy thinned and fragmented, organic input to the forest floor declined, reducing the resource base that had supported high densities of large detritivores. Arthropleura, with its high absolute resource requirement, a function of its large body mass, was more sensitive to this decline than smaller detritivores that could subsist on reduced organic input. The elevated atmospheric oxygen that had permitted giant arthropod body sizes was itself beginning a long decline during this period as carbon burial rates decreased with forest fragmentation and as the gradual evolution of more effective lignin decomposing fungal lineages allowed greater proportions of dead plant material to be oxidatively decomposed rather than buried. The decline in oxygen was slow, operating across millions of years rather than thousands, but its direction was consistent. For organisms at the upper size limits permitted by tracheal respiration at a given oxygen concentration, even a modest decline in that concentration translated into a meaningful reduction in the physiological ceiling on body size. Populations of giant arthropods faced not only declining food resources, but a gradually contracting atmospheric envelope within which their body plans could function. The large temnospondyle amphibians of the permanent swamp systems faced a different but related set of pressures. Their reproduction, like that of the lycopod trees, depended on standing water. Eggs were laid in aquatic environments, and larval stages were obligately aquatic periods, as permanent swamp water bodies became smaller and more isolated under the increasingly variable Carboniferous Permian climate. The reproductive habitat available to large temnospondyls contracted. Isolated water bodies also concentrated predators and competitors in smaller areas, intensifying intraspecific competition and potentially driving cannibalism rates upward as prey availability declined relative to predator density. Dispersal between isolated water bodies represented an additional challenge for large, water-dependent tetrapods. A temnospondyl of 1.5 meters body length, crossing dry forest floor to reach a distant water body, faced physiological constraints on the duration of such a crossing. Water loss through the skin, elevated body temperature on exposed ground, and the energetic cost of locomotion on terrain for which its body plan was not optimally configured. Smaller, more physiologically flexible tetrapods, including early amniotes, whose reduced skin permeability and water-conserving physiology had been refined for exactly these conditions, could traverse dry intervals that effectively isolated large temnospondyls in shrinking refugia. The concept of ecological specialization as vulnerability is illustrated clearly by the fate of the Carboniferous giants, organisms that had achieved large body size, complex ecological dependencies, and narrow physiological tolerances under the stable conditions of the Carboniferous peak were, by definition, organisms whose evolutionary histories had not included selection for flexibility under variable conditions. Their adaptations were precise solutions to a specific set of environmental parameters. When those parameters shifted, the precision of their adaptations became a liability. The same morphological and physiological features that had made them effective in stable conditions made them inflexible in changing ones. The evolutionary response to environmental change requires heritable variation in relevant traits and sufficient time for selection to act across generations. For organisms with large body size, long generation times, and low population densities, conditions that characterize many of the Carboniferous giants, the rate of evolutionary response was slow relative to the rate of environmental change. What the fossil record documents from this period is not a sudden mass extinction, but a protracted ecological unraveling, the progressive disappearance of the most specialized and least flexible components of the Carboniferous ecosystem, beginning at the margins of their ranges and contracting toward the remaining core habitats where conditions most closely approximated those under which their adaptations had evolved. The giants did not vanish in a geological instant. They persisted in refugia, declined in abundance, and were progressively replaced by organisms whose physiological flexibility and reproductive independence from standing water equipped them more effectively for a world that was becoming, by measurable and inexorable degrees, less like the one that had produced them. Mayu said, "Continue but max 7,000 characters." The physical evidence for Carboniferous forest collapse is preserved in sedimentary sequences across multiple continents, with a clarity that makes the transition one of the better documented ecological events in the Paleozoic record. In coal-bearing formations of Europe and North America, the boundary between continuous Carboniferous coal seams and the overlying sedimentary layers of the early Permian is marked by a structural change in depositional character that reflects a fundamental shift in the terrestrial environment. Below the boundary, thick, laterally continuous coal seams record the sustained accumulation of organic material in permanent, waterlogged conditions, the physical signature of stable lycopod swamp forest operating at high productivity across large connected basins. Above it, coal layers become thinner, more discontinuous, and interbedded with clastic sediments, sandstones and mudstones deposited by rivers and wind that indicate the progressive replacement of permanent swamp conditions by seasonally dry, hydrologically variable environments. This transition, termed the Carboniferous rainforest collapse by researchers working on its documentation and causes, did not occur uniformly across all affected regions simultaneously. The sedimentary record indicates that collapse proceeded at different rates in different basins, influenced by local topography, proximity to moisture sources, and the specific trajectory of regional climate change. Some basins show an abrupt transition, compressed into a relatively short stratigraphic interval, suggesting rapid local habitat loss. Others show a more gradual change spread across a longer depositional sequence, consistent with a slower deterioration of swamp conditions. This spatial heterogeneity in the timing and rate of collapse had significant consequences for the biological communities affected. It determined which populations were extirpated rapidly and which persisted in refugia long enough to potentially adapt or disperse. The plant communities that replaced lycopod-dominate swamp forest in the post-collapse landscape were structurally and ecologically distinct from their predecessors. Seed plants, including early conifers, seed ferns of lineages different from those present in the Carboniferous swamp forest, and early cycad relatives, were better equipped for the drier, more seasonally variable conditions of the early Permian. Their reproductive biology, based on seeds rather than spores, was fundamentally less dependent on standing water. Seeds encapsulate the embryo and its initial nutrient supply within a protective coat that tolerates desiccation, allowing dispersal across dry terrain and germination when moisture conditions become favorable rather than requiring continuous moisture availability. This reproductive flexibility gave seed plants a decisive colonization advantage in the fragmented, seasonally dry landscape that followed lycopod forest decline. The transition from spore-based to seed-based plant dominance was not simply a replacement of one set of species by another ecologically equivalent set. It was a functional reorganization of the terrestrial plant community, with cascading consequences for every organism that depended on plant-derived resources. Lycopod trees, with their rapid growth, high biomass production, and continuous organic input to the forest floor, had sustained the detritivore community at a productivity level that seed planter communities of comparable area could not immediately replicate. The structural complexity of the lycopod forest, its multiple vertical layers, its dense canopy, its persistent standing water, created microhabitats that the more open, structurally simpler early seed plant communities did not reproduce. Organisms dependent on those microhabitats faced not just reduced resource availability, but the physical disappearance of the habitat configurations their body plans required. Food chain disruption propagated upward through trophic levels as the base of the ecosystem contracted. The detritivore community of the forest floor, already stressed by declining organic input and fragmenting habitat, supported the secondary consumers that preyed upon it, small tetrapods, arachnids, and predatory myriapods. As detritivore biomass declined, the predators dependent on it faced reduced prey availability, driving either population decline or behavioral shifts toward alternative prey. Alternative prey, in a contracting ecosystem, was itself under pressure. The compounding effect of declining productivity at multiple trophic levels simultaneously, what ecologists describe as a trophic cascade operating in reverse, accelerated the rate of community integration beyond what the direct effects of habitat loss alone would have produced. Aquatic food chains underwent parallel disruption as water bodies shrank and became isolated. Permanent swamp channels, which had provided stable aquatic habitat across large connected areas, fragmented into smaller, disconnected pools and seasonal wetlands as the groundwater table declined, and surface drainage patterns became more episodic. Fish populations in isolated water bodies faced the same genetic and demographic constraints that affect any population confined to a small, bounded habitat: reduced gene flow, increased vulnerability to local extinction from stochastic events, and reduced capacity to recolonize following local population crashes. The large temnospondyle predators dependent on productive, permanent aquatic systems found their habitat contracting into a diminishing set of viable locations. The atmospheric oxygen decline that accompanied forest fragmentation interacted with the biological community changes in ways that compounded the pressure on giant arthropods. As oxygen concentrations fell from their late Carboniferous peak, the physiological ceiling on arthropod body size descended correspondingly. Populations of large arthropods faced a shrinking atmospheric envelope simultaneously with declining food resources and fragmenting habitat. The combination of these pressures, no single one of which would necessarily have been fatal in isolation, created a convergent stress regime in which the probability of population persistence declined across multiple independent parameters simultaneously. Extinction in this context did not necessarily mean the disappearance of entire lineages in geological instance. For many of the specialized Carboniferous organisms, the process was one of range contraction, the progressive abandonment of marginal habitats as conditions deteriorated, withdrawal toward core refugia, where conditions remained closest to the ancestral optimum, and eventual disappearance when even those refugia became inhospitable or too small to sustain viable populations. The fossil record captures this process as a decline in the geographic and stratigraphic range of affected taxa, specimens becoming rarer, geographically more restricted, and associated with increasingly marginal depositional environments as the Carboniferous Permian transition progressed. The forests that remained in the early Permian were shadows of their Carboniferous predecessors in terms of structural complexity, areal extent, and the ecological diversity they supported. The continuous green canopy that had stretched across the equatorial lowlands for tens of millions of years had been replaced by a fragmented, structurally simpler vegetation cover in which the dominant plants were physiologically better, adapted to variability but ecologically less productive in absolute terms. The transformation was not the end of terrestrial plant life or of complex terrestrial ecosystems. It was the replacement of one ecological configuration by another, driven by the intersection of biological processes and physical planetary change. What it ended, permanently and without reversal, was the specific set of conditions that had made the Carboniferous forest the most productive and biologically extreme terrestrial ecosystem that Earth had yet produced. The disappearance of the Carboniferous giants from the fossil record was not a single event with a defined date. It was a drawn-out process of population attrition, range contraction, and final extirpation that unfolded across the Carboniferous Permian boundary interval and continued into the early Permian, spanning several million years of progressive ecological deterioration. The giants did not go together. They went separately, at different rates, from different causes, in different parts of a landscape that was itself undergoing continuous structural transformation. What the fossil record documents is a sequence of absences, the last appearance of one taxon, then another, that collectively describe the dismantling of an ecological community whose component parts had been assembled across tens of millions of years under conditions that would not recur. Arthropleura, the largest terrestrial invertebrate in Earth's documented history, disappears from the fossil record during the early Permian. Its last confirmed occurrences are from deposits formed under conditions still partially consistent with the humid, organic-rich environments it required. Transitional habitats that preserved some of the structural character of the Carboniferous swamp forest while exhibiting the reduced permanence and increased climatic variability of the post-collapse landscape. The absence of Arthropleura from younger deposits is not an artifact of preservation bias in any obvious way. The sedimentary environments that would have captured its trackways and body fragments continue into the Permian, and the tracks simply are not there. The animal had ceased to exist as a functioning population before those sediments were laid down. The physiological logic of Arthropleura's extinction is consistent with the environmental changes documented for this interval. Its large body mass required a continuous and substantial supply of plant material in various stages of decomposition. Its tracheal respiratory system required atmospheric oxygen concentrations sufficient to supply interior tissues through passive diffusion. Its reproductive biology, like that of modern millipedes, involving direct development without a water-dependent larval stage, was less constrained by water availability than that of the temnospondylus, but its foraging requirements tied it to habitats with high organic productivity. As the forest floor environment became drier, less continuously productive, and more structurally simple under the expanding seed plant communities of the early Permian, the resource base that could sustain a 2.5-meter high biomass detritivore contracted below the threshold necessary for viable population maintenance. The giant flying insects of the Carboniferous, the Dragonflies and their relatives, show a similar pattern of decline, with maximum body sizes decreasing through the late Carboniferous and earliest Permian before the lineage disappears entirely. This size reduction is itself informative. It suggests that the population was not simply extirpated suddenly, but was responding to changing conditions over multiple generations, specifically to declining atmospheric oxygen concentrations that progressively lowered the physiological ceiling on tracheal respiration. As oxygen fell, the largest individuals in the population, those operating closest to the diffusion limits of their respiratory systems, became progressively less viable, and the mean body size of surviving populations shifted downward. The trajectory of size reduction through time, preserved in the size distributions of fossils from successive stratigraphic levels, traces the retreating atmospheric envelope within which these animals could sustain flight and reproduction. The loss of large-bodied aerial predators from the Carboniferous airspace removed a selective pressure that had influenced the evolution of smaller, flying insects for tens of millions of years. The escape behaviors, flight patterns, and morphological features of smaller insects that had evolved under consistent predation pressure from griffinfly scale predators were no longer being maintained by that selection pressure. This release from predation pressure contributed to a restructuring of the aerial insect community during the early Permian, not an immediate transformation, but a gradual shift in the distribution of body sizes, flight behaviors, and ecological roles among flying insects as the dominant selective force that had shaped them was progressively removed. The large temnospondyle amphibians, whose ecological dominance in permanent swamp systems had persisted through the Carboniferous, faced a more complex extinction trajectory than the giant arthropods. Some temnospondyle lineages proved more adaptable than others, and the group as a whole persisted well beyond the Carboniferous Permian boundary. Some lineages surviving into the Triassic and even the Cretaceous in restricted form. But the specific ecological configuration of the Carboniferous, large, permanently flooded lowland basins supporting apex temnospondyle predators at high population densities, was not replicated in the Permian. The temnospondyls that survived did so in reduced ecological roles, in more restricted habitats, and at body sizes that reflected the diminished productivity and spatial extent of the aquatic systems available to them. The giant swamp predators of the Carboniferous were replaced not by ecologically equivalent successors, but by a fauna organized around fundamentally different principles. The ecological vacuum created by the disappearance of giant arthropods and large amphibian predators was not immediately filled by equivalent organisms from other lineages. Ecological vacuums of this magnitude, the removal of dominant functional groups from large areas of habitat, typically produce transitional periods of reduced ecological complexity before successor communities establish themselves. The early Permian terrestrial ecosystem in the areas formerly occupied by Carboniferous swamp forest was characterized by lower species diversity, simpler trophic structure, and reduced biomass productivity relative to the ecosystem it replaced. Recovery, in the sense of re-establishment of complex, multi-layered ecological communities, would eventually occur, but through a different set of organisms operating under different physiological and ecological principles, producing an ecosystem that shared few specific components with the Carboniferous system it succeeded. The early amniotes, the small, physiologically flexible vertebrates that had established themselves in the dry forest interior during the Carboniferous, were among the few vertebrate groups that navigated the Carboniferous-Permian transition without severe reduction in diversity or ecological scope. Their independence from standing water for reproduction, their reduced skin permeability, and their capacity to exploit the seed plant communities expanding across the drying landscape gave them access to resources and habitats that became progressively unavailable to water-dependent competitors. Through the Permian, amniote lineages diversified rapidly into the ecological space, vacated by declining amphibians and giant arthropods, producing the radiation of reptile and synapsid forms that would eventually give rise to dinosaurs, mammals, and the full diversity of modern terrestrial vertebrates. What ended with the Carboniferous giants was not simply a collection of large-bodied species. It was an ecological configuration, a specific arrangement of atmospheric chemistry, plant community structure, and biological diversity that had no precedent and has had no recurrence. The elevated oxygen that permitted giant tracheal respiration, the continuous lycopod canopy that sustained the forest floor community, the permanent swamp systems that supported apex amphibian predators. These were not independent features that happened to co-occur. They were components of an integrated system, each dependent on the others, each reinforcing the conditions that made the others possible. When the system began to fail, it failed as a system, its components declining together, their interdependency becoming liabilities rather than supports, as the environmental foundation on which all of them rested was progressively withdrawn, you said. You skipped chapter 11, do that, but max 7,000 characters. The Carboniferous forest vanished as a functioning ecosystem more than 300 million years ago, but it did not vanish without trace. Its physical remnants are distributed across the continental interiors of Europe, North America, and Asia in the form of coal seams, compressed, chemically transformed accumulations of organic material that represent the single largest repository of biologically fixed carbon in Earth's geological record. These seams, ranging from centimeters to tens of meters in thickness, preserve within their structure and chemistry a detailed record of the biological processes that produced them. They are not simply fuel deposits. They are archives, imperfect, incomplete, but recoverable, of an ecosystem whose surface expression disappeared long before the first human observer existed to record it. The process by which living forest became coal operated across three distinct stages separated by geological time. The first stage was peat formation, the accumulation of partially decomposed plant material in anaerobic, waterlogged conditions that inhibited the microbial oxidation which would otherwise have returned organic carbon to the atmosphere. Carboniferous peat deposits, some reaching thicknesses of tens of meters before compaction, formed in the permanently flooded basin environments where lycopod trees grew and died in continuous succession. The second stage was diagenesis, the physical and chemical transformation of buried peat under increasing temperature and pressure as overlying sediment accumulated across millions of years. Water and volatile compounds were progressively expelled, carbon content increased as a proportion of total mass, and the original plant material was converted first to lignite, then to bituminous coal, and in areas of greatest burial depth and tectonic pressure, to anthracite. The third stage was exposure, the tectonic uplift and erosion that brought coal-bearing strata to depths accessible to surface mining and geological investigation. Within coal seams and the sedimentary layers immediately associated with them, preservation of biological material occurs through several distinct mechanisms. Compression fossils, flattened impressions of plant material in fine-grained sediments, preserve the external morphology of leaves, bark surfaces, and reproductive structures with sufficient detail to allow taxonomic identification and morphological analysis. Coal balls, calcareous nodules that formed through early diagenetic mineralization of plant material before compaction, preserve three-dimensional cellular anatomy in extraordinary detail, allowing researchers to reconstruct the internal structure of Carboniferous plant tissues at the level of individual cells. These coal ball specimens, sectioned and examined under transmitted light microscopy, have provided much of the foundational knowledge of Carboniferous plant biology that underpins current understanding of the ecosystem. Animal material is preserved less commonly than plant material in Carboniferous coal-bearing sequences, a reflection of the taphonomic bias toward organisms that were numerically abundant, structurally robust, and frequently deposited in environments conducive to preservation. Arthropod exoskeletons, composed of chitin, a structurally resistant biopolymer, survive diagenesis more effectively than soft tissue, and compression fossils of cockroach-like insects, fragmentary myriapod remains, and occasional arachnid specimens have been recovered from fine-grained sediments associated with coal seams across multiple European and North American sites. Vertebrate material, while less common, is represented by fragmentary tetrapod bones and, at exceptional sites like the Joggins Formation in Nova Scotia, by articulated or semi-articulated specimens preserved in 3 dimensions within interior cavities of upright lycopod stumps. The Joggins Formation represents one of the most scientifically significant Carboniferous fossil sites currently known. Designated a UNESCO World Heritage Site in 2008, its coastal cliff exposures, extending approximately 15 kilometers along the shore of the Bay of Fundy, present a continuous stratigraphic section through Carboniferous sediments that preserves an integrated record of plant, communities, animal assemblages, and depositional environments across several million years of the late Carboniferous. The upright lycopod stumps preserved in growth position within these cliffs allow direct reconstruction of forest structure, tree spacing, and canopy height. The fauna preserved within stump cavities provides spatially constrained ecological data. The organisms recovered from a single stump represent a biological community associated with a specific habitat at a specific moment in geological time, rather than a time-averaged assemblage from a larger depositional area. Trace fossils, the preserved evidence of biological activity rather than the organisms themselves, contribute an additional category of information about Carboniferous ecosystem function. Arthropleura trackways, preserved in fine-grained sandstone and siltstone at multiple sites, record not only body size, but locomotor behavior, the spacing between footfall, impressions, the width of the trackway, and the curvature of the path all provide data about the animal's gait, speed, and response to substrate features at the moment of preservation. Burrow structures preserved in Carboniferous sediments record the 3-dimensional architecture of subsurface habitats constructed by invertebrates whose body fossils may be absent from the same deposits. Root trace fossils, the preserved outlines of root systems penetrating into sediment below ancient soil surfaces, allow reconstruction of plant, community density and root architecture in areas where above-ground plant material was not preserved. Geochemical analysis of Carboniferous materials has opened additional lines of investigation that complement morphological fossil evidence. Carbon and oxygen isotope ratios preserved in carbonate nodules and organic material provide information about ancient atmospheric composition, temperature, and the metabolic pathways used by specific plant lineages. Biomarkers, specific organic molecules whose chemical structures are resistant to complete degradation and whose biological sources can be identified, survive in coal and associated sediments and provide evidence of the microbial and biochemical processes operating in Carboniferous environments. Nitrogen isotope ratios in fossilized organic material offer constraints on trophic position. the level at which an organism fed within the food web, providing ecological information that morphology alone cannot supply. The scientific reconstruction of the Carboniferous ecosystem from these multiple lines of evidence is not a completed project. New fossil sites are identified through geological survey and erosion of previously buried strata. New analytical techniques. High-resolution computed tomography scanning of three-dimensional specimens, synchrotron-based imaging of compression fossils, increasingly precise isotopic and biomarker analysis continue to extract information from existing collections that earlier methods could not access. Each new data point refines or revises the picture of the ecosystem in ways that occasionally confirm existing models and occasionally require their substantial modification. What the accumulated evidence describes is an ecosystem of a character and scale that the modern world does not replicate. A forest covering tens of millions of square kilometers, producing oxygen at rates that altered planetary atmospheric chemistry, sustaining animal communities whose body sizes have not been equaled by any subsequent terrestrial arthropod fauna, and burying carbon in quantities whose geological legacy continues to shape human civilization. The coal seams beneath the industrial heartlands of Europe and North America are not merely economic resources. They are the compressed physical remains of one of Earth's most extraordinary biological episodes. A record written in carbon, preserved across 300 million years, and still being read. You said, continue but max 7,000 characters. 307 million years ago, in a forest that covered a significant fraction of the Earth's equatorial surface, the biological processes that had operated continuously for tens of millions of years were still running at their full Carboniferous intensity. Lycopod trees rose to 50 meters in stands so dense that their canopy formed a near-continuous surface across the lowland basins. Giant arthropods moved through the organic-rich darkness of the forest floor. Dragonflies crossed the airspace above the canopy on wingspans wider than a human arm span. Temnospondyls held position in dark swamp channels, their lateral line systems registering the pressure disturbances of approaching prey. The atmosphere above it all contained oxygen at concentrations that the planet has not seen since. The system was, by any measure, at its maximum expression. Nothing in the biological or physical record of this moment indicated the trajectory that followed. The peat continued to accumulate. The lycopod spores continued to disperse across standing water surfaces. The organic carbon continued to be buried faster than it could be decomposed. The atmospheric oxygen continued its slow rise. The system gave no signal of its own impending transformation. Not because the forces driving that transformation were absent, but because they operated on timescales that no organism within the system could perceive or respond to within a single lifetime, or 1,000 lifetimes, or 1,000,000 years of lifetimes. The forest end, when it came not as catastrophe but as arithmetic. The glacial cycles intensified. The dry intervals lengthened by fractions of a degree and a few weeks of reduced rainfall per cycle. The permanent water bodies shrank by meters at their margins. The lycopod recruitment rate fell below replacement by amounts too small to measure in any individual location across any individual year. The organic input to the forest floor declined gradually enough that no single detritivore populations experienced a threshold event, only a slow, continuous reduction in the resource density on which it depended. The system did not break, it drained. The organisms living through this transition had no awareness of it as a transition. A temnospondyl occupying a shrinking swamp channel in the early Permian was not experiencing the end of the Carboniferous. It was experiencing a drought, a season, a year of reduced prey availability, conditions that its behavioral repertoire was equipped to navigate in the short term. The difference between a temporary drought and the permanent restructuring of a planetary ecosystem is not detectable from within a single organism's experiential horizon. The animals of the late Carboniferous and earliest Permian lived and died in specific places at specific moments, responding to immediate conditions with the behavioral and physiological tools their evolutionary histories had provided. That those tools were increasingly mismatched to the trajectory of change they were embedded in was a fact, visible only from the perspective of geological time. What the forest left behind, beyond the coal seams and compression fossils and trackway impressions already described, was a set of evolutionary consequences that extended forward through all subsequent terrestrial life. The amniote lineage that had established itself in the dry forest interior during the Carboniferous carried forward the physiological and reproductive innovations that the forest's own climate variability had selected for. The early synapsids and sauropsids that diversified through the Permian and Triassic were biological products of the Carboniferous forest in the most direct sense. Organisms whose foundational adaptations had been shaped by selection pressures operating within that ecosystem and in response to its collapse. The mammals and reptiles of the modern world are, in their reproductive biology, their skin permeability, and their independence from standing water, the inheritors of solutions to problems that the Carboniferous forest posed. The insects that survived the end of the Carboniferous giants were smaller, physiologically constrained by declining oxygen and released from the predation pressure that griffin fly scale predators had imposed for tens of millions of years. Their subsequent diversification, the explosive radiation of insect lineages through the Permian, Triassic, and beyond that eventually produced the approximately 1 million described insect species of the modern world, proceeded in the absence of the atmospheric conditions that had briefly permitted gigantism. The insects of the modern world are the descendants of Carboniferous survivors, shaped by the same tracheal respiratory system that once permitted wingspans of 70 centimeters, now operating within the constraints of a 21% oxygen atmosphere that limits that same system to the body sizes observable today. The coal beneath the surface of the modern world preserves the chemical energy of Carboniferous sunlight. Photons that struck lycopod leaves 300 million years ago were converted into chemical bonds through photosynthesis and have remained sequestered in sedimentary carbon ever since. The forests that captured that energy were themselves products of atmospheric and geological conditions that will not recur. The specific convergence of lignin biochemistry, fungal decomposer limitation, tectonic basin configuration, and equatorial climate stability that produced the coal measures was a singular event in Earth's history, not a repeating cycle. The carbon buried in the Carboniferous will not be buried again by an equivalent process. The modern forests that cover portions of the Earth's equatorial regions are, in some structural respects, the most distant functional analogues of the Carboniferous ecosystem still in existence. They are warm, productive, vertically stratified, and biologically diverse. They cycle carbon and produce oxygen through the same biochemical processes that the lycopod forests employed. They sustain large arthropods, though none approaching Carboniferous dimensions, and complex predator-prey communities organized around the same trophic principles that governed Carboniferous food webs. But they are not the Carboniferous forest. Their dominant plants reproduce by seed rather than spore. Their arthropod fauna is constrained by 21% atmospheric oxygen to body sizes orders of magnitude below the Carboniferous maximum. Their decomposer communities are functionally complete, returning organic carbon to the atmosphere efficiently rather than burying it. They are ecosystems operating under a different set of parameters, producing different outcomes in a world that the Carboniferous forest itself transformed. The last lycopod forests disappeared from the geological record during the early Permian, replaced by seed plant communities across the basins where they had grown continuously for tens of millions of years. The replacement was not marked by any visible boundary in the rock. No impact layer, no ash horizon, no geochemical spike. Only the gradual change in the types of plant fossils present in successive sedimentary layers and the thinning and eventual absence of coal seams records the transition. The forest ended the way it had existed, quietly, continuously, at a pace determined by the slow variables of atmospheric chemistry and climate, leaving behind, in the compressed carbon of its buried remains, the most durable record it could produce of the time when it covered the world. 9.